In this video, we're going to look at series. Exactly what is a series? Well, it goes back to an infinite sequence. If we have an infinite sequence, then an infinite series is the sum of all the terms. And you may ask yourself, how are we going to add an infinite amount of things and actually get an answer? Well, you've done that before when you were doing integrals. Remember, we took all of our little rectangles and we added them up and we let n approach infinity, and so we had an infinite amount of rectangles and we got the area under a curve. So you can indeed add an infinite amount of things and get a finite sum. Now, as you're going to see, we don't always get a finite sum, and that's really the whole thing of this chapter. We're going to look at things and see if they converge or diverge. But I'm a little ahead of myself. So in order to find the sum of an infinite series, how we are going to do that is we're going to look at the sequence, which remember is the list, of partial sums. And if the sequence of the partial sums converges, then the series converges. So what are partial sums? It just means that the first partial sum is just really the first term. The second partial sum is adding the first two terms. And then we'd add up the first three terms. And then we're going to add up the first n terms and see if that approaches a certain value. In other words, does the sequence of partial sums converge to a particular value? So let's look at these two examples and just look at their partial sums. So I have this series, 1 over 2 to the n. So remember, you're going to let n equal 0, 1, 2, 3, 4, and so forth. So it would go on forever. But let's look at those partial sums. So the first partial sum is just the first term. The second one is adding the first two terms together. The third is, of course, adding the first three terms together. And I'm going to do one more. So adding up the first four terms. And I believe if you add that up, you get 15/8. So the question is, do we see some pattern? Could we possibly write these sums in terms of a formula, if you will? Well, we could observe that 1 is the same as 2 minus 1. 3/2 is 2 minus 1/2. 7/4 is 2 minus 1/4. 15/8 is 2 minus 1/8. Do you see a pattern there? Sure you do. So 2 minus 1 over 2 to the what power? Well, let's see. When n was 1, we had 2 maybe to the 0 power. When n was 2, we had 2 to the first power. When n was 3, we had 2 squared. So we might say that that is 2 minus 1 over 2 to the n minus 1 power. So is this sum, is this sequence of partial sums, is it converging to a value? In other words, the limit as n approaches infinity of s sub n, what is that going to be? Well, you should know as n approaches infinity that that's going to go to 0, and so our sum is 2. So what we can conclude is therefore the series of 1 over 2 to the nth power converges to the sum of 2. And that's what we are going to be investigating. So if we have an infinite series, we can get the sum if the limit of the sequence of partial sums, and that's why there's an n there, as n approaches infinity. If that limit exists, then we can say the series converges to a sum that we're just going to use s. Let's just try one more. See if we can see if this infinite series converges, and if it does, what does it converge to? So we can see we've written out some of the terms, keeps going forever. So what's the first partial sum? Is a half. The second, 1/2 plus 1/6, what's that going to be? 2/3. Then we have 1/2 plus 1/6 plus 1/12, and believe it or not, that's going to be 3/4. So 1/2 plus 1/6 plus 1/12 plus 1/20, what does that equal? I believe it's 4/5. So again, do we have a pattern? Could we possibly see that? Okay, so what do we have? We have 1/2, 2/3, 3/4, 4/5. Keep going. Is there a pattern to these? Remember, it's a sequence, so that's why I'm making a list of partial sums. Well, if I look at the numerator, is that not just our n values, n starting going from 1 to infinity? And this is 1 bigger. So can I find the limit as n approaches infinity of s sub n? What's the limit of that? You have the same power over the same power, so you could use L'Hopital's rule, but it really, just go back, you should see that the limit is equal to 1. So we could say, therefore, this infinite series, as k goes from 1 to infinity, converges, and it converges to a sum of 1. So if we add up the infinite amount of terms, we get a sum of 1. So to try to sum that up, for a convergent series, its sum is defined as the limit of its partial sums. So we have a sum as n approaches infinity is the sum of the partial sums. In other words, if the sequence of partial sums converges to our s, then our series converges. And of course, s is just the sum. On the other way, if the sequence of partial sums diverges, in other words, that limit does not exist, then we would say the series diverges also. Sometimes it is very difficult to find what that sum is. Every once in a while we can see the pattern, but sometimes we just can't. The good news is there's some specific types of series that we can easily find the sum and calculate that sum. One of which is the geometric series. So a geometric series is a sum of terms where each term is multiplied by the same value. And we're going to call that same value r, which is the common ratio. So if I just keep multiplying by r, I would get these terms. Of course, our a can't be 0, because then you would just be adding up a bunch of zeros. A is the first term, r is the common ratio. Now you should have seen this probably in a pre-calculus class. So let's just kind of go see if we can be familiar with a geometric series. So here our first term, of course, would be 5. But what is r? What are you multiplying by each time? 3. So we want to put our r, I like to put it in parentheses just to make sure we're not messing up on our order of operations, and then this would be to the n minus 1 value. I will say, be careful. Check that index. When I plug in 1 there, do I get this first term? Does 5 times 3 to the 1 minus 1 power equal to 5? Yes, it does, because that's 1. Remember, 3 to the 0 or anything to the 0 power is equal to 1. Okay, let's look at the next one. Obviously, our first term is 1/3. But what are we multiplying by each term? We've got negative, positive, negative, and so forth. What's going to make it go from negative to positive, negative to positive? A negative value. So we're multiplying by 1 on top. What are we multiplying by on the bottom? 3. So again, if I put that to the n minus 1 power, I want to check that out. So if I plug in 1 1/3 times negative 1/3 to the 1 minus 1 power. Does that equal to my first term? Yes, it does. So that's good. Now, I want to throw this in. Even though this is a correct answer, I could have written it this way. And sometimes this is what you're going to encounter. Lots of different correct answers. See if that would work. If I plug in 1, do I get 1/3? If I plug in 2, do I get negative 1/9? If I plug in 3, do I get positive 1/27? And yes, you do. So I want you to kind of look and see how the heck could you have gone from this answer to this answer. Something to think about. Now, of course, this whole chapter is going to be whether the series converges or diverges. So if I have this geometric series, I want to know, when will it converge or diverge? Is it consistent every time? Well, I think it's going to depend on what that value of r is. What are we multiplying by? Because remember, a is just a constant. So what happens if I multiply everything by just 1? Okay, so if I take that series, a plus a times r plus a times r squared plus a times r cubed and so forth, what are you going to get? You're going to get a bunch of a's, right? An infinite amount of a's. So if a was 2, you'd have 2 plus 2 plus 2 plus 2, so forth. If a was 1/8, you'd be adding up an infinite amount of numbers. What's going to happen? What would you conclude? Well, you could go back and say, well, the sum of the first partial sums is a, the second one would be 2a, the next one would be 3a, so n of n would be n times a. And what would happen as the limit approached infinity? The limit does not exist because this would just go to infinity, so this diverges. So we can say that geometric series diverges when r is equal to 1. What about negative 1? So what happens when r is equal to negative 1? What would that series look like? Well, we would have a plus a times negative 1 plus a times negative 1 squared plus a times negative 1 cubed, so forth. Does this converge to a sum? Well, you might think, well, maybe they'll add all out and you get 0. Well, let's look at the sequence of partial sums. So the first sum would be a, the second partial sum would be a minus a is 0, the third, you would get a, the fourth one, we get 0. Now we definitely see a pattern. The question is that pattern converging? Well, the first one was a, the second one's 0, the third one's a, the fourth one's 0, so it's not converging. It's oscillating between 0 and a, 0 and a. So we would say the limit as n approaches infinity of these partial sums does not exist. It diverges. So we have a geometric series that we know does not converge if a is 1 or negative 1. So we could keep trying a bunch of different values. Let's go at it a little bit more scientific. As in, what about other values of r? So here is my infinite series. What happens if I multiply all of them by r? So each term times r. So this would become this, and then we have r squared, and so forth. And of course, when I multiply a times r minus 1 times r, remember that's to the first power, I would keep the base and add the exponent, and that's how that gets there. Why am I doing that? Just give me a minute. So now what happens if I subtract these? If I have s sub n minus r times s sub n. Well, if I subtract, then all of those would become minus. Well, that minus that would go, disappear, add to 0, and so forth. And so the only thing that you would be left with would be those two terms. So we'd have a minus a times r to the nth power. Okay, now you say so. Well, remember, we're trying to find what our sum is. So that's s sub n. So what if I factor out s sub n? That would leave me 1 minus r, because there's a 1 in front of that. And if I divide both sides by 1 minus r, well, right there, that tells me r cannot equal to 1 because I cannot divide by 0. So the sum of the sequence of partial sums could be given as this formula. I'm going to factor out the a of 1 minus r to the n power. So we know r can't equal to 1. But I want to know what happens when n is infinity. What is the sum of the infinite series? In other words, the limit as n approaches infinity. Well, let's see. The only place we have an n is right there. So I'm going to have this as a times 1 minus the limit as n approaches infinity. And let's see what happens there. So we know that r cannot be 1 because of the division. Remember, we also found out that this certainly doesn't converge if r is negative 1. And let's see why that is. Because if r is negative 1 raised to the nth power, again, we'd have negative 1, positive 1, negative 1, positive 1, and we would reach that same conclusion as we did before. So what's going to make that converge? What happens if the absolute value of r is bigger than 1? So if we have a really big number being raised to an nth power, wouldn't that diverge? But what happens when the absolute value of r is less than 1? As n approaches infinity, we have a number less than 1, 7/8, 3/4, getting raised to a power of n. That's going to approach 0. So we could say the limit as n approaches infinity of s sub n is equal to the sum of a over 1 minus r as long as the absolute value of r is less than 1. Keep that in mind. That means from negative 1 to positive 1, but not including negative 1 and positive 1. And that's what's kind of neat about geometric series. We actually can find the sum as long as this is true. So again, in conclusion, the series converges if the absolute value is less than 1, and we're going to go ahead and put this, it diverges if the absolute value of r is greater than or equal to 1 everywhere else.